And welcome to part 2 of lesson 2. So the last video we wrapped up, we were talking about strongest reducing agents and going down to weakest reducing agents. So we looked at 4 reactions, and in these 4 reactions, the metal ions are the oxidizing agents, and the silver ion is the strongest oxidizing agent, is the SOA. So we're going to just put on the highlighter here. The silver ion is the strongest oxidizing agent because it is the most reactive in our group. The two lists can be summarized using a single set of half reactions. All right. So the decreasing reactivity of oxidizing agents is over here. On the side, we have the decreasing reactivity of reducing agents. All right. So our SOAs, our strongest oxidizing agent is Ag+, and our strongest reducing agent is zinc solid. And what that means is that zinc solid wants to undergo oxidation to cause something to be reduced. Ag+ wants to be reduced in order to have something undergo oxidation. All right. In table 3, the metal ions are on the left side of the equations. And the metal atoms are on the right side. Yep. All right. For metal ions, the oxidizing agents over here. The half reaction equations are read from left to right in the table. For metal atoms, the reducing agents, the half reaction equations are read from right to left. So that's why we have these arrows here, and we're going to talk a little bit more about this in our next unit, which is equilibrium, how reactions can go back and forth. But essentially, these are happier, this is happier to go this way, this is happier to go this way. That does not mean that this can't go this way and this can't go this way. However, though, for now, we're going to stay with the understanding that these want to go in accordance to the green lines that I just put in. All right. We're going to go back to this table here. It's already filled in here this time around. And what we have is using our reduction table, we know that Ag+, which if it is right here, and that is Ag+, and we have zinc solid here, and we have zinc solid here, it is a spontaneous reaction. And again, we know that Ag+ was spontaneous with everything, and we know that zinc solid was spontaneous with everything. Ones like copper, though, this is where it kind of gets a little confusing, is because copper 2+, oops, I shouldn't use green if we're already using green. We'll go with purple. Copper 2+ is happy to react with lead solid. We go copper 2+, lead solid, spontaneous. However, though, if we switch that around, I don't want to use red. I need a really funky pen color. I'm green. All right. If I have lead 2+, though, and I have copper solid, we look at our copper solid, our lead 2+, what we see in the corresponding box is it's non-spontaneous. All right. So when we go look at this, we're just going to hop back just as a quick reminder for ourselves, in which we had our strongest oxidizing agents there. So SOA and SRA here. All right. So our strongest oxidizing agent has to be over our strongest reducing agent for it to be spontaneous. All right. Just give me one moment here and let me see if I can go not have much luck here. All right. Let's see. All right. Here we go. I have my pen. So we're going to put SOA over SRA. And I'm going to put an arrow and do this in crayon. All right. I hate that. It is spontaneous. All right. If we have our SRA, our strongest reducing agent, over our strongest oxidizing agent, this reaction is, it'll be non-spontaneous. All right, that's just a side note about this chart here, which we've added more information to. Hopefully this is starting to make sense. Please do send questions my way via email, on Google Classroom, or wherever works for you. Okay, we're gonna hop on to our Venn diagram here. So some generalizations can be made about what type of entities are oxidizing agents, reducing agents, or it can be both. So oxidizing agents, they're usually cations, which are metal ions, non-metal atoms, and acidic solutions. Reducing agents are anions, non-metal ions. So for instance, anything in any of our non-metals, so like chlorine, oxygen, any of that, metal atoms, and basic solutions. And then we have this category of both. And what you'll see is Fe2+. And the reason Fe2+ is in that both column category is because if it goes and becomes an atom, it can become a really good reducing agent, which is Fe solid. And it can also become an oxidizing agent, which is Fe3+. All right. We're going to talk about your redox table. So I hope you have your chemistry data book with you. I can also upload a digital file, including one, if you need one. So your redox table. There's a larger redox table made from the data of hundreds of experiments done over time found on page 7 of your data booklet. So this isn't the full page. It does cut off here at sulfur solid reacting with hydrogen. However, though, this is what it looks like in your data book. So again, we have our SOAs here going down, and we have our SRAs here going up. And we're going to talk more throughout this unit about what things like the electric potential mean and how this works more and more. Right. We're going to talk about the spontaneity rule. So we've already talked about this a little bit. Maybe I got ahead of myself, but the spontaneity rule is the redox spontaneity rule states that a spontaneous redox reaction occurs only if the oxidizing agent OA is above the reducing agent RA in a table of relative strengths of oxidizing and reducing agents. We've already done that. Made this page here. I'm hopping back though. Uh-oh, did I get myself lost? Oh, there we go. All right. So our oxidizing agent has to be above our RA. So I will do this here. If that's the case, we get a spontaneous reaction. If our oxidizing agent is under our reducing agent, then it's a non-spontaneous reaction. Oops, I'll leave that there for just a moment, just so you can kind of analyze that a little more. And what you'll see is below that, predict if a reaction will occur between the following reactants. So you're going to use the table here, and you need to predict whether we will have a spontaneous or non-spontaneous reaction. So our first one is lead and F2. Go up to our table, and we find F2, which is here. And then we also have lead solid, which when we go onto our table, and what we begin to see is that lead is not on this image here. But what you can do is you can go to your data book And what you will do is you will see lead solid is further down on the right-hand side of the arrow. So it is a reducing agent, and we'll find that lead is over here. The question is this is my oxidizing agent F2, and this here is my reducing agent. Now, we take a quick look again at the spontaneity rule. Is my oxidizing agent above or below my reducing agent? The oxidizing agent is above the reducing agent. What that means is that we have a spontaneous reaction. All right. So right there, spontaneous. The next one you have is solid zinc and water. All right. One of the issues we're going to find is that this does not include our full data table, but what we do find is that this is a non-spontaneous reaction. And be careful. One of the other things to note is that, but H2O is here, right? However, that is H2O reacting with water. We want H2O on its own reacting with an electron. So what ends up happening is that when we find H2O on its own, it is down here somewhere. It's a liquid because it is water. But we find out that it is below zinc. And because of that, it will be not spontaneous. All right, the last one is the same thing. Tin is not on there, but Ag plus is a really good oxidizing agent. So this one is spontaneous. All right, this is going to be our last little bit here of the lesson here today. And then I'm not going to do the second example, and then you will be able to do practice sheet 3. All right. So for our last bit here, the spontaneity rule gives us another way of creating a redox table. So we have 3 reactions here, and 2 of which are spontaneous, 1 of which is non-spontaneous. All right. We know that if we go back, our oxidizing agents want to undergo reduction, and they usually have a charge. All right. So we have ions on this side, and we're often going to have atoms on this side. Now, when we look at our first reaction here, we have CO2 plus reacting with iron solid, and the reaction is spontaneous. What that means is that this is our oxidizing agent, this is our reducing agent, and the second one also spontaneous, which means that this is CO2 plus is our oxidizing agent, and CO is our reducing agent. And then in the bottom one, it's non-spontaneous. However, though, Cu2 plus is our oxidizing agent, and PD solid is our reducing agent. All right. Now, the information we can get from this is that, let's start with our last one here. When Cu2 plus reacted with PD solid, what we found out is that PD solid has to be higher as a reducing agent than Cu2 plus is as an oxidizing agent. So we know that PD solid is going to be at the top or very close to the top of our table. All right. One of the other things too is, do we know the charge of PD? We can take a look at our data books. It is PD2 plus. So PD2 plus 2 electrons. All right. What else have we found out here? Well, we know that if we go to our first one, iron solid becomes iron 3 plus. Because it jumps from an atom to a 3 plus ion, it is actually going to be at the bottom of our table, of our redox table. All right. we said that will be IN solid. And then it is IN 3 plus 3 electrons. Now we have the middle two, which is Cu2 plus and CO solid, which we know that it's a spontaneous reaction when Cu2 plus is the oxidizing agent. So Cu2 plus has to be above CO solid. So I can set this up like that, and I'll fill in my arrows here. And then I can put my copper solid plus CO2 plus, and these will both be 2 electrons plus 2 electrons. Again, the reason I was able to do that and not the other way around is because CO2 plus is our OA, our oxidizing agent, and IN solid is, or sorry, I'm on the wrong one here. CO2 plus is our oxidizing agent, and CO solid is our reducing agent. We go back to our spontaneity rule, and our SOA has to be above our SRA in order to be spontaneous. So when we go back to this slide here, what we can say is that Cu2 plus has to be above CO in order for it to be spontaneous, as pointed out here. There is an second example. I'm going to wrap up here. If you have any questions, please ask on the classroom. Send me an email, joshua.wallace@aspenview.org. And in practice sheet 3, one of the things I have done is I'm going to do about 1 example per section, just so that way we can cut down on some of the time. You are supposed to be spending 3 hours per course per week, so that kind of cuts us down from our regular 5 hours a week. However, though, I think I've kind of exceeded that a little bit because those videos the other day were a little lengthy. All right. Again, please do ask questions if you have any. And I think the next few days, make sure you get that assignment 1 done. And then we'll likely be able to have an assignment later this week, but maybe we'll do that early next week. All right. Have a great day, and we'll catch up with you later.